Okay, in the last lecture we studied the exponential function, which was denoted e power x, and we learned also the inverse of the exponential function. What is the inverse of the exponential function? What is it called? What is the inverse of an exponential function? It is the logarithmic function. Okay, so when you have an exponential function with the base e, the inverse of that the inverse of that function is the logarithmic function, which is denoted len x. Okay, and for the function e power x, the inverse of that function is called log base a x. Okay, so these are two basic functions that we need to know. They are very basic functions in any applications in engineering. We must have these kind of functions. Okay, one application of the exponential function is the definition of a new kind of function, which is called hyperbolic functions. Okay, first let us know what is a hyperbola. A hyperbola is some sort of curve, and we learned about it in the algebra section or the analytical geometry section. It is a curve like that. This purple curve is called hyperbola. Okay, we will learn about that. This is one of the conic sections, one of the known conic sections. We will learn more about it in analytical geometry section. However, the equation of this hyperbola is much like the equation of a circle. It is x squared minus y squared equal to 1. Okay, we have learned before the unit circle. We learned before what is called the unit circle. Okay, the unit circle has an equation like this. The unit circle had an equation x squared plus y squared equals 1. Okay, so that equation is much like the equation of the unit circle. This is called the unit hyperbola. Okay, this is the unit circle. If we remember, we defined some sort of functions depending on the unit circle, and we called them circular functions. What were these? These were the trigonometric functions. If you remember that the coordinates of a point moving on a unit circle, they are just cosine of the angle and sine of the angle. So this is the angle theta. Okay, so whenever you are moving on the unit circle, the coordinate changes according to cosine theta and sine theta. So the circular functions, or cosine theta and sine theta, are the coordinates of a point moving on a unit circle. Okay, so let us define a new kind of functions, for which are the coordinates of a point, instead of moving on a unit circle, they are moving on a unit hyperbola. Okay, they are moving on a unit hyperbola, and we will call them hyperbolic cosine and hyperbolic sine. Instead of these cosine and sine, which are known to be circular functions. Okay, so we will define them like this. We say that this is cosine alpha. This, note how it is pronounced, cosine alpha, or in some universities it is cos h. Cos h is cosine hyperbolic. The h corresponds to the word hyperbolic. Okay, and we have sine alpha. Okay, it is pronounced in Alexandria University to be shine. In some other universities, it is pronounced to be sin h or sin sh. Okay, there are many pronunciations for the same function, but in Alexandria University, we just call it cosine and sine. Cosine and sine. Okay, so these are the new coordinates for a point moving on the unit hyperbole, just as an analog to the circular functions or the trigonometric functions which were cosine theta and sine theta. Okay, now but there is a question here. What does this alpha correspond to? We learned before that cosine theta and sine theta, this is just the angle. But what about in this case? What is alpha in this case? Now, this might not be much obvious, but if we take a straight line to the origin and we calculate this area, so this area will just be half of alpha. So what is alpha? Alpha, it is just the double of that green area. What is alpha? It is double of that green area. Okay? Now, this definition for the alpha, it is much like an analog definition, but for theta. Okay? Let's consider this section of the circle. What is the area of this section? What if I had a circle with a radius r, okay, and I took a section with angle theta? Do you remember the rule for the area of that section? What is the rule for the area of that section? The area is just half of r squared theta. Half of r squared theta. Okay? So when we have a unit circle, we have r to be equal to 1. If we have a unit circle, we have this to be 1. So what is the area in the case of the circle? It is just half of theta. Okay? So this definition is much as an analog to this definition too. If you take a straight line to the origin and you calculate this black area will just be the double. Sorry, it will just be half of the parameter that you are talking about. So in this case, it will be theta over 2. The area of this black part will just be half of theta, or half of the parameter. So in both cases, we have the function, the parameter is just double of that area. When you connect the point to the origin and you calculate the area to the x-axis, so that area is just half of the parameter. Or in other words, the parameter is just double of that area. Okay? So in both cases, we have an analog definition also, but in circular functions or in cosine and sine, a more obvious definition for the parameter is just the angle theta. Okay? But this other definition with respect to the area or in terms of the area is analog in these two functions. Okay? So that is the hyperbolic cosine and hyperbolic sine, which is called cosine and sine. Okay? Now, because cosine theta and sine theta are coordinates of a point on a unit circle, we learned a first basic rule for cosine and sine, which comes from the equation of the circle, which is cosine squared theta plus sine squared theta would just equal to 1. What would you expect the basic definition or the basic rule for the hyperbolic functions? Now this point satisfied the equation of the circle, of the unit circle. And we learned that hyperbolic functions, these two hyperbolic functions satisfy which equation? Satisfy the equation of the unit hyperbola. So we will expect that cosine squared alpha minus sine squared alpha will be equal to 1. Okay? And this is the analogous rule for that one. That is the analogous rule for the hyperbolic function, analogous to that rule in circular function or in trigonometric functions. Okay? Now let's look on the definitions of these points. We'll define cosine x to be equal to e power x minus or plus e power minus x over 2, and sine x to be equal to e power x minus e minus x over 2. Okay, this is not the only definition that I may define for a point on a hyperbola. I may, for example, define any base for that function. But for convenience, we just learned that a best expression for an exponential function is to make the base to be equal to e. That is more convenient for us. When we learn about differentiation, we'll learn that derivative or the differentiation of this function is just the same as it is. But for any other exponential function, d by dx of e power x, that will be as it is, but it will be multiplied by some constant, so that may cause some inconvenience for us. So that's why they have chosen the definition to be in terms of the exponential or the natural number e. So it is e power x plus e power minus x over 2. And sine x is just e power x minus e power minus x over 2. This is a definition for the cosine and sine. Okay? This is also an analogous definition for some other definition for trigonometric functions. Okay? Now, but it depends on the complex analysis, which defines the root of -1 to be some number I. We'll define it by I. Okay? Now, this is called complex analysis. When we treat this as a number, the root -1 as a number, and we call it I, this is called complex analysis. In our study, we are just confined to real analysis, not complex analysis, but I'm just giving you an idea for where would these two definitions come from. Okay? Now, in complex analysis, there is a fundamental rule which states that it is called Euler formula. Euler formula. Euler formula states that e power I theta is equal to cosine theta plus I sine theta. That formula is a fundamental rule in complex analysis, and it was discovered by Euler. Okay? If we put theta substituted to be negative theta, we will get another formula, which will be e power minus I theta to be equal to cosine theta. But if you take the minus inside the sign, it will be taken out, so it will be minus sine I sine theta. Now, if you add these two equations, you will get that 2 cosine theta is just equal to e power I theta plus e minus I theta over, and if you divide by 2, so that will be 2 like this. And also we'll get that sine theta will just be e power I theta minus e minus I theta over 2i. Okay? So this Euler formula have helped us to make definitions or make relations between trigonometric functions and the exponential. Look at these two definitions, or look at these two relations. We'll find that cosine How would we relate the cosine to the exponential? They are related to each other, and the sine with the exponential, they are related to each other, but in terms of that definition for the root minus 1. Okay? Cosine theta is just equal to e power I theta plus e power minus I theta over 2, and sine theta is just e power I theta minus e minus I theta, but over 2i instead of 2. So when we thought of hyperbolic functions, we looked for a just similar definition to be related to the exponential, but without these i's. So it is just an interesting definition to have definitions much like these, but without the i's or without the root of -1. Okay, so these are just definitions which are much like the definitions of cosine and sine in terms of e, okay, but without the complex basic number which is root -1. Okay, so these two are called cosine and sine. Now we'll define the other hyperbolic functions in just the same way we defined trigonometric functions. For example, if we need to define what is tan x, tan hyperbolic, or tan h, or tanh, okay, it is defined to be sine x over cosine x, which it would be, can be written as e power x minus e minus x over e power x but plus e power -x. Okay, so this is the definition of tan x. We may also define cotang x, which is just the reciprocal of tan x. It will just be the reciprocal of tan x. What about, we will have also sech x. It is just 1 over cosine x. It is just 1 over cosine x, or the reciprocal of cosine x. What about cosech x? It is just 1 over the sine x. It is 1 over sine x. Okay? So these are the definitions of hyperbolic functions. We have three basic hyperbolic functions and the reciprocals of these three basic hyperbolic functions. Okay? Now let's return to these cosine x to be e power x plus e minus x over 2, and sine x is just e power x minus e minus x over 2. Okay, now these two definitions must be memorized. We'll just need them in our problems. Now let's derive some rules. Okay, one first rule: what if we add up these two definitions? What is cosine x plus sine x? What is cosine x plus sine x? Now if we add up these two equations, we'll just find that these two terms will be cancelled. Okay, so we'll have e power x over 2, e power x over 2 added to each other, which will just give me e to the power x. Okay, so the sum of cosine and sine, it is just the exponential function. What about if we subtract these two functions? If we need to find what is cosine x minus sine x. So in this case, we'll find that these first two terms will cancel, and we'll get e power negative x. We'll get e power negative x. Now you need to remember, could e power negative x, could it have a negative value? Can you remember what is the range of such function? the range of the output or the output of an exponential. Could you remember? Could this, what about this number? Is it a positive number, or it is 0, or it is a negative number? E power negative 1. Now remember that this is the graph of e power x. And so the graph of e power negative x, which would be just a reflection of that above curve, this is e power negative x. Okay, so both e power x and e power negative x have a range. What is the range of any of these two? It is just the positive numbers. It is just the positive numbers. So an exponential function is never negative, and it is also never 0, unless you put an input to be in infinity. And infinity is not a number, but you may take it as so this number is a positive number. This number is a positive number. So what does it mean if you have that cosine x minus sine x is a positive number? It means that the cosine is just greater, will be always greater than sine x. If you subtract two functions and you say to me that one of them is greater than the other by this quantity. So it means that this positive quantity. If the subtraction is always a positive quantity, so this one will be, or the difference is a positive quantity, so this function is greater than the other by just that quantity. Okay? So we'll always have cosine x to be greater than a sine. A cosine is always greater than a sine. Okay. Let's learn. So these are the first two basic rules. These are the first two basic rules, and we don't have analogous rules for them, or we didn't learn analogous rules for them for trigonometric functions. For example, we didn't learn what is cosine theta plus sine theta in terms of exponential. They have an expression which is e power I theta. Okay, but we are not having our study in complex analysis, so we didn't learn that expression or that rule before. But in general, we don't have these expressions, or we didn't learn an analogous for these two expressions in trigonometric functions. But any of the other trigonometric relations that we have learned in trigonometric functions, we will have an analogous form for it for hyperbolic functions. We have just stated the analogous for sine squared x plus sine plus cosine squared x equal to 1. We had an analogous form for that in the hyperbolic functions, which was that sine or cosine squared x minus sine squared x, it will just equal to 1. Okay, let's write it in the similar way. That is cosine squared x plus sine squared x equal to 1, and that came from the equation of the unit circle, and that equation is just satisfying the equation of the unit hyperbola. Okay? Now, there is a rule that lets me to know the analogous rule for any trigonometric rule that I have learned before. For example, I have learned that 1 plus tan squared x is just equal to sec squared x. There is some analogous rule for this other rule, but in hyperbolic functions. What is that rule? It is if you find two sines multiplied by each other, if you find two signs multiplied by each other, you change the sign of that term. Change sign of that term. If you find two signs multiplied by each other, or if you find two tans multiplied by each other. Okay? So whenever you find a rule for trigonometric functions which has two signs multiplied by each other or two tans multiplied by each other, in this case we just interchange the sign of that term. So that's why for that rule I have just found this term. This term is just two signs multiplied by each other. So that's why the analogous rule for hyperbolic functions, it was just cosine squared minus sine squared. Okay? I have just changed the sign for this term. So let's look at this. Let's look at this rule. What would be the analogous rule for this one? Now, do I have two signs multiplied by each other or two tans multiplied by each other? Yes, I have that second term. That second term is just two tans multiplied by each other. So I would expect the analogous rule to be like that. 1 minus tan squared x. That to be equal to, does sec squared have two signs or two tans multiplied by each other? No. So it will just remain, its sign will just remain as it is. So it will be sec squared x. Okay? So what about this rule? 1 plus cotan squared x, it is just equal to cosec squared x. What is the analogous of this rule? It is just, so do I have two tans multiplied by each other in this rule? Yes. Inside the cotan squared, two cotans multiplied by each other are just the reciprocal of two tans multiplied by each other. So I will just interchange that term, then change the sign of that term. Do I have any other two signs or two tans multiplied by each other? Yes. That term also, for that term, that is cosec squared. They are just the reciprocal of two signs multiplied by each other. So that's why we'll also interchange the sign of this term. So what would be the analogous rule for that one? It will just be 1 minus cotan squared x. It is just equal to minus of cosec squared x. Okay? And so on for every rule that you have learned in trigonometric functions. Okay? These rules just, this basic rule applies for any rule that you have learned in trigonometric functions. Double angle relations, for example, you learned that cosine squared x is just cosine 2x. You have just learned that cosine 2x, it is just cosine squared x minus sine squared x. What would be the analogous rule for that one? It is just cosine 2x, it is just equal to, would I change the sign of that term? No, it will just be as it is. So it is cosine squared x. What about that term? Would I change its sign? Yes, I would change its sign because it's two signs multiplied by each other. So it will be cosine squared plus sine squared. Okay? So cosine squared plus sine squared, that is exactly cosine 2x. What about this rule? We learned that cosine 2x, it is just equal to 2 sine cosine. What would be the analogous rule for that one? It will just be sine 2x. Now, do I have here for sine 2x equal to 2 sine cosine? Do I have two sines multiplied by each other or two tans? No, I don't have. So I wouldn't interchange any sign for that rule. It will just be sine 2x. It is just equal to 2 sine x cosine x. Okay? Now, by the way, the argument of hyperbolic functions, it is not an angle. Okay? It is just a number. We learned before that trigonometric functions, the argument or what is inside the sine or cosine, it is called an angle. This is called an angle. What is inside the sine and the cosine. Okay? It is called an angle. And we learned that in angles we may measure it by radian or by degree and so on. But what about this one? The argument of hyperbolic functions. The argument of hyperbolic functions, it is just a number. Okay? Why? Because it is just exponential functions. They are just defined as exponentials. So whenever I say, for example, cosine 1, what is cosine 1? Cosine 1, it is just e power 1 plus e power negative 1 over 2. And these are just numbers as they are, and we don't call it an angle. But as a metaphor for the angle, we will call it a hyperbolic angle. Okay? In definitions, or more rigorously, we will not say that this is an angle. But for just simplicity and for the analogy with the trigonometric functions, I may say that what is inside the hyperbolic functions is an angle or an hyperbolic angle. Although you know in your mind that it is not an angle. Okay? It is just, so we don't have radian or degrees. If you take your calculator and you put it in the mode of radian or in degree and you calculate cosine 1, calculate it in the mode of radian and calculate it in another time in the mode of degree, you will get the same result. But if you put cosine 1 in the calculator in the two modes, yes, you will have two different, in this case you will have two different results. Why? Because it makes a difference if you treat that one as radian or if you treat it as degrees. Okay? Because this is an angle in this case. This is an angle. But this is a number and it doesn't make a difference for us even if it was radian or if it was degree. Okay? But I may sometimes say the argument of cosine and sine, I may say it, although it is not 100% correct, I'll just say that it is an angle or an hyperbolic angle, but you have in mind that it is not an angle. I'm just saying that by analogy to the trigonometric functions. Okay? If you continue for the rules, for example, if we know the rule of the addition of two angles, which is cosine A plus B, it is expanded as cosine A cosine B minus sine A sine B. What would be the analogies for this rule? So that will be cosine A plus B will be equal to, I have here two cosines multiplied by each other, so I wouldn't change the sign for that term. It will just be cosine A cosine B. Okay? Now for that term, would I change the sign for that term? Yes, I will change the sign, so it will be plus sine A sine B. It is plus sine A sine B, and so on. So whenever you know that shortcut, and whenever you know the rules of trigonometric functions, for each law of trigonometric functions, you will just find the analogous rule for the hyperbolic functions. But you must keep in mind, for example, we learned rules of cosine, for example, of pi over 2 minus x. What was that in trigonometric functions? Cosine pi over 2 minus x. Could you remember? We used this rule in simplifications of inverse. With inverse trigonometric functions, we learned that cosine pi over 2 minus x is just the sine of x. Okay? So would I have a rule like this in trigonometric functions? Could I say that it would be cosine pi over 2 minus x would be equal to sine x? No. This is not One would say we don't have here two sines or two tans multiplied by each other, so I wouldn't change any. The sign of any terms. So he would write it like this. No, this is an incorrect formula. Why it is incorrect? Because this rule just comes from this rule. If you expand that side, what would it give us? It would just give us cosine pi over 2 cosine x plus sine pi over 2 sine x. And it just happened that cosine pi over 2 is 0 and sine pi over 2 is 1. So that's why the result was sine x. So if you need to know the analogous rule for cosine pi over 2 minus x, it would just be cosine pi over 2 cosine x plus sine pi over 2 sine x. It will just be, no, so it will just be with negative sign here. It will just be, it will just be like that. But in this case, cosine pi over 2 and sine pi over 2 are not 0 and 1 like trigonometric functions. These are just e exponentials, e power pi over 2 minus plus e power negative pi over 2, and this is not equal to, so this is not equal to 0. This is not equal to 0 and this is not equal to 1. Okay? So we will not have a simple expression like that for hyperbolic functions. What is the correct expression for cosine pi over 2 minus x? It would just be that whole expansion as we did as an origin for this rule. Okay? So we have learned, by now we have learned how to find the analogous of any trigonometric rule that I've learned before in trigonometric functions. So let's consider the graphs of hyperbolic functions. The graphs of hyperbolic functions. We'll learn to graph the cosine x and sine x. Cosine x is sketched like this, and sine x, this is cosine x, and sine x is just graphed like this. So you might notice that just like the trigonometric functions, cosine of 0 equal to 1, just like that cosine 0 equal to 1. And we'll find that sine 0 is just equal to 0. Sine 0 is just equal to 0. Just like that sine 0 is equal to 0. So we may have some similarity in that point. For the origin, it is just much similar to the trigonometric functions. Okay, but it differs much afterwards for any other value instead of the, or any other value other than the origin. The curve will change dramatically. It wouldn't be like the cosine and sine. You will lose the property of periodicity. You don't have any, the cosine and sine were periodic functions. Why would trigonometric functions be periodic? That because trigonometric functions came from a circle, and whenever you are moving on a circle, you will just repeat yourself every 2 pi. Every 2 pi you will just repeat yourself. But in an hyperbolic curve like this, whenever you are moving on the hyperbola, you will not repeat yourself. So you have lost the property of periodicity. The hyperbolic functions are not periodic. Hyperbolic functions are not periodic. Okay? Now you might notice that cosine x must be, it is a great value. Cosine x, it is the greatest, it has the greatest value among all other hyperbolic functions. It is greater than the sine, it is greater than the tangent, it is greater than sec and cosec. So it is just greater than any of these. It is the greatest among the hyperbolic functions. Okay? Now you'll just notice that cosine x, what is the range of that function? The output of cosine must be greater than 1. So it is not just positive. It is not just positive. It is also greater than 1. A cosine always have a great value. Okay? So it is greater than 1 or equal to 1. What about the domain of cosine? It is just R. So there are no conditions to what is inside the cosine. And so for the sine, the domain is just R. What about the range for the sine? The output of the sine, do I have any condition for the output of the sine? No, we don't have any conditions, so we just find that it is also R. Also R. What about the symmetry? What about the symmetry of each of these two functions? What is the symmetry? It is if the function is even or odd. So what would you expect in this cosine x? Is it even or odd? Cosine x from the graph. Do you find any symmetry in the graph of cosine? I need your interaction with me. Do I have any symmetry in this curve? Yes, I have a symmetry about the y-axis. I have symmetry about the y-axis. So it is what is a function that is symmetric about y-axis? It is an even function. So a cosine is an even function. Cosine is an even function. Cosine x is an even function. What does it mean to be an even function? It means that whenever there is a negative inside the cosine, you can remove it. It will be like this. We say that as if cosine has eaten the negative sign inside it. As if the cosine have eaten most likely the cosine x. Okay? So cosine x, we have a similar property with the trigonometric function. A cosine is also an even function, like the cosine x. So what about the sine x? Do I have any symmetry in this curve? Do I have any symmetry? Yes, we have a symmetry about the origin. Whenever I have a point here, there is another similar point on the other side like this. So it is symmetric about the origin. What is a function that is symmetric about the origin? It is called an odd function. So we have that sine x is an odd function. What does it mean to have an odd function? It means that sine of negative of anything, we just take out the negative sign. The negative sign may be taken out the odd function like this. What about the property of 1 to 1? We need the property of knowing if it is 1 to 1 to find the inverse. What about cosine x? If you look at this curve, is it 1 to 1 or not? It is not 1 to 1. Not 1 to 1. Why? This is from the horizontal line test. It doesn't satisfy the horizontal line test. So it is not 1 to 1. What about sine x? Is it 1 to 1 or not? Yes, it is 1 to 1. The horizontal line test, it is satisfied. So it is 1 to 1. Okay, and we learned before that whenever a function is not one-to-one, it doesn't have an inverse. It is not invertible. Unless I may choose a restricted domain for which I may define the function to be one-to-one and also covers the whole range of the function. Okay? We have learned before how to find an inverse for a function that is not one-to-one by a suitable restricted domain for which we may redefine the function to be one-to-one and cover the whole range for us. But shine x, as we'll know that it is completely invertible without any restrictions in the domain. As it is, we'll find that it is invertible. If we like to graph both of the functions cosine and sine, I've just learned this is the cosine. If we plot or depict the sine on the same plane, we'll just find the sine to be like this. As you may notice that it is always the difference between cosine and sine, that difference, it is just e power negative x. It is a positive value. That's why cosine is always greater than the sine. Cosine is always greater than the sine. So we have learned about cosine x and sine x. Let's learn about tanh x. Let's learn about tanh x. Now tanh x, we have just learned that tanh x is just sine x over cosine x, which may be, by using the main definition, we'll just substitute to be e power x minus e power negative x over e power x plus e power negative x. Now I may find another equivalent formula. If I just multiply the numerator and denominator by e power x. If I just multiply the numerator and denominator by e power x, so I will obtain that new formula. I may write it as e power 2x minus 1 over e power minus 2 over 2 e power 2x plus 1. But if we multiply the numerator and denominator by e power negative x, if I multiply by e power negative x, I will just get another equivalent formula, which is 1 minus e power minus 2x over 1 plus e power minus 2x. So these three formulas are just equivalent to each other. These three formulas are just expressing the tanh of x. And I need to know the three formulas for tanh x. Okay, I need to know the three formulas for tanh x. Now, let's graph tanh x. But before graphing tanh x, let's look at some points. For example, some main points. What about tanh 0? Tanh 0, I've just learned that it is sine 0 divided by cosine 0. What is sine 0? It is just 0. What is cosine 0? We learned that it is 1. So tanh 0 is just equal to 0. Tanh 0 is just equal to 0. So we have the origin is one of the points of tanh. Much like the sine or the sine. What about tanh of infinity? What about tanh of infinity? Now I need to substitute with infinity. And we learned before, what is e power infinity? If I have this graph for e power x, what is e power infinity? For x approaching infinity, the value of e power x will just go to infinity. It will just grow indefinitely. So it will be infinity. What about e power negative infinity? If you go to the left side for the negative infinity side, You will just find that the exponential will just decay until it be 0. Okay, it will just decay to be 0. So it will just approach 0. And you may look at it as 1 over e power infinity. When we learn that this is just infinity, so 1 over infinity is just 0. Okay, so I need to substitute for infinity in that expression. If you use the first expression, you will get something like this. It will be e power infinity minus e power negative infinity, e power infinity plus e power negative infinity. And we learned that e power negative infinity is just 0. But e power infinity is just infinity, so I'll just get infinity over infinity. And this is called undetermined quantity. This is not a number. I cannot, or this is a number that I cannot I cannot manage to find it by this only information. So this is not a suitable expression to put or to substitute with infinity. Which of these three expressions would you expect to be more suitable to substitute with infinity? If you substitute with infinity in the second expression, I will just get e power infinity minus 1, e power infinity plus 1. I will just get again infinity over infinity. But what if you use the third expression? I will just get 1 minus e power negative infinity over 1 plus e power negative infinity. That is 0 and this is 0, so I'll just get 1. I'll just get 1. So that's why we have a horizontal asymptote. This is called an horizontal asymptote for the positive side. The curve of tangent will just be like this. And it is just approaching, this is that red straight line. It is called an asymptote. What is an asymptote? It is a line for which the curve is approaching, but it never touches it. Or you may say that it touches it. It touches it in infinity. Okay. We also need to find tangent of negative infinity. You may use it, the second expression for this one. You will get that it is exactly negative 1. What would you expect tangent x to be for the symmetry of tangent? Would it be an even function or an even function? An odd function or an even function? From this definition, we learned before that sine is just an odd function, and the cosine, we learned that cosine is just an even function. Okay? So when you divide an odd function by an even function, you get an odd function. So tangent is just an odd function. And so that's why if you have tangent negative infinity, you can take the negative outside, so it will be just minus tangent of infinity, which is 1, so it just gives me negative 1. And I may also expect it to be an odd function. It will be symmetric about the origin, so to complete the curve, it will just be like this. So this is the curve of tangent x. This is the curve of tangent x. It is the range. Its range is from negative 1 to 1. Now, if you look at some similarities with former curves that we have learned before. For example, the curve of cosine x, it is much like a curve that we have known before, which is x squared, and for more accuracy, it is x squared plus 1. If you graph this function, x squared plus 1, you just get a curve which is much like the cosine x. Okay? And what about the sine x? What is it it is like? Sine x, it is like a curve that we have learned before, which is x cubed. X cubed, the power function, which is much like the sine x. What about this curve? We learned before a curve which looked like this. Could you remember? What was the curve which looked exactly like this? Not exactly, but it just has the same shape. It was the tan inverse x. If you remember the tan inverse x, was just like this from negative pi over 2 to pi over 2. Okay, and the curve was just like this. Tan inverse x was just, it is much like the curve of tanh x. Okay? Now let's look at this problem. We will need to learn a skill. If I am given some hyperbolic function, I need to find the other related hyperbolic functions. For example, for this, if it is given that sine x is equal to negative half, what is cosine that x and what is tanh of that x? If you remember, for trigonometric functions, if I told you that sine x is equal to half, so what is cosine x and what is tan x? How would you solve that problem? When I tell you that sine x is equal to half, and I need to find cosine x and tan x, one most popular method to find this angle is by the triangle. If you say this is x, so the 1 over 2, and that will be 4 minus 1, which is 3. So if you told me that sine x is equal to half, the cosine x will just be equal to root 3 over 2, and the sine x will be equal, and tan x will just be 1 over root 3. Okay? But these are not the only solutions. Why? Because when I tell you that sine x is equal to half, in this case, we will have two basic angles. Do you remember that in the unit circle, when I tell you I need to find the angle which has a sine which is equal to half? In this case, we will have two basic angles, this angle and that other angle, that was sine inverse half, and the other was pi minus sine inverse half. You need to remind yourself with the solutions of trigonometric functions. We had two basic angles. Okay, so for this equation, when I say to you sine x is equal to half, this is equivalent to two angles. So when I say that, this solution is just for angle if the angle is in the first quadrant. But you need to study what if the angle was in the second quadrant. If it was in the second quadrant, you will find the cosine will just have a negative value. It may have a negative value also. So that's why it is cosine x in this case will be plus or minus root 3 over 2, and that also will be plus or minus 1 over root 3. This is based on your understanding of this relation. This relation is an expression for two angles, not one. For two basic angles, not one. So that's why we may have two values for these two functions, cosine x and sine x. And you may derive these two values, or you can obtain these two values from the rules of cosine and sine. For example, you know that cosine x, it is just the square root, or you know that cosine squared, it is just equal to 1 minus sine squared. So, and you have the sine, so that will be 1 over 4, that will be 3 over 4. So cosine squared is equal to 3 over 4. That means that the cosine will be plus or minus root 3 over 2. Okay, and that plus or minus, it just means that this first, that given, that corresponds to two angles instead of one. So that's why we had two values for the cosine and the tan, because these are just two values for these are just two angles. What about if I had an expression like this? Now in this case, could I have a triangle? No, because as you have learned, this is not an angle, and I don't have a triangle in this case. Okay, so a standard way to find the solution of this problem is to use the rules. For example, instead of using that rule, I would use that cosine squared x is equal to 1 plus sine squared x. Now remember that the cosine was the greatest among the hyperbolic functions, so that's why I told you that 1 plus, I just add a 1 to the sine to get the cosine. Okay, that is how I memorize it. I remember that the cosine is the greatest, so I just say that 1, I need to add 1 to the sine squared to get the cosine squared. Okay, so I may say that I know that cosine squared, so cosine squared x, it is just 1 plus negative half squared. So that will be 1 plus 1 over 4, which is just 5 over 4. But in this case, when I take the square root, cosine x, it is plus or minus root 5 over 2. But if you remember, could a cosine have a negative value? No, we learned that a cosine always have not only a positive value, it is a value that is greater than 1. A cosine must have a value that is just greater than 1, not only positive, not only I reject any negative value. Not only I reject negative values, I reject any positive value that is less than 1. Okay? So that's why I reject that negative sign. And for this case, I will find that cosine x will just be equal to root 5 over 2. Cosine x will just be equal to root 5 over 2. And so I will find that sine x is just equal to the tangent. I need to find the tangent. What is tangent x? Tangent x, it is just the sine x over cosine x. So I may divide these two values. So it will be negative half over root 5 over 2. So that will just be exactly minus 1 over root 5. Now there is a rule that we may need, that we learned that tangent x is just sine x over cosine x. And we learned that cosine x is always a positive value. So that means that tangent always have the same sign, as sine. So whenever I had sine x, for example, if sine had a negative value like this, I would expect the tangent will have also a negative sign. Whenever a sine had a certain sign, if it was negative, for example, the tangent will have a similar sign, which is a negative also. Okay? But this is not the only method. Actually, I managed, as a student like you, I have managed to find a method by making use of some sort of triangle. To make it easy, it is just attractive to find a solution using a triangle like this in trigonometric functions. So, as a student, when I was in your age, I have just managed to find a method, an alternative method, without using the rules or the laws of trigonometric or hyperbolic functions to find the solution of such a problem. Let's rewrite the problem. I have here sine x to be equal to negative half, and I need to find cosine x, and I need to find tangent x. Okay? To find the solution using a triangle, I will not use the regular triangle. I will choose some other form of a triangle, which is called a fake triangle. And to characterize it, or to make it different from the regular triangle, I will just highlight that side like this. The adjacent side, I will just highlight it like this. Okay? I will just write that expression, sine x equal to 1 over 2, so that will be 1 over 2 like this. It will be 1 over 2 like this. Now, I need to complete the triangle. Now remember, this is called a fake triangle. It is just an imaginary triangle, not a real one. How would I find that side? I will just find it by treating it as the largest side among the three sides. Now remember, in a regular triangle, what was the greatest side? It is always the hypotenuse, okay? So that, for a regular triangle, the hypotenuse was the greatest, okay? What if you treat that side as the greatest? What would be the result? In this case, it will just be the square root. If it is what the greatest, it would be square root of 4 plus 1. So it is just root 5. Okay? Now remember, this is a fake triangle. It is not, these values do not, we just make a use of the rules of triangle to find these values. So whenever I made that fake triangle, I may now find cosine x. So what is cosine x in this case? Cosine x, it is just the adjacent over the hypotenuse. It will just be root 5 over 2. What about tangent x? Tangent x, which will just be the opposite divided by the hypotenuse, which will just be half. Sorry, it is the opposite divided by the adjacent, so it will be 1 over root 5. And remember the rule that a tangent has the same sign as the sine. So that's why it will have a negative sign like this. It will have a negative sign like this. Okay? Now let's compare these two values with the values that we have got from the rules. We'll find that cosine x equal to root 5 over 2, which is exactly like this, and tangent x, which was also equal to minus 1 over root 5, which is exactly like this. Okay? So that is how we may find, given some hyperbolic function, we may find all the other hyperbolic functions from a fake triangle in this way. Okay? What, for example, if I told you that tanh x is equal to negative half? If I told you that tanh x is equal to negative half, find sine x and cosine x. Now let's use the fake triangle, and putting in mind that a tanh has the same sign as the sine, or the sine will have a same sign as the tanh, and the cosine will always be positive and greater than 1. Okay, so let's make the fake triangle, which I would highlight the adjacent side. Tanh equal to 1 over 2, it will just be like this. So how would I complete that triangle? Would it be 1 plus 4? No. I just treat that side as the greatest among them. So what would be that side? It would just be 4 but minus 1, yes. So that will be root 3. That will be root 3. So that's why if you need to find sine x, for example, sine x, it will have a negative sign at the tanh. Okay, that is one. The second is that what is the sine? It will just be 1 over root 3. And for the cosine, it will just be cosine x, it will just be 2 over root 3. Okay, so whenever you depicted the fake triangle, you may find any of the hyperbolic rules, hyperbolic functions. Now for this case, what is given is cosine x equal to 3 over 2. Now just pay attention that this is a value that is greater than 1. A cosine is always has a value that is greater than 1. Now when I tell you that cosine x is equal to 3 over 2, what is sine and tanh? So that corresponds to that fake triangle, which is 3 over 2. What would be the missing side? What do I write here? Root. What is the number that I write inside the root? Would it be 13 or would it be that would be, yes, 9. That I treat that as the greatest among them. So it would be 9 minus 4. It would be 9 minus 4. So that's why it is root 5. So that's why we say that sine x in this case it will be root 5 over 2, and tanh x in this case it will just be root 5 over 3. But there is a flaw in this solution. Yes, what about the negative? Yes, if you look at this equation, we learned that cosine x has this curve. So whenever I give you some value for the cosine, for example, that is 3 over 2, how many x's does this statement correspond to? How many x's? That gives me that if I have cosine x equal to 3 over 2, I would have two x's that satisfy this equation. Or I may say it as if it is two angles. Okay, they are not angles, but we will just, as a metaphor for us, we'll just say that it is an hyperbolic angle. We have two angles corresponding to this statement. Just like when I told you, when I talked about the this trigonometric relation, I told you that this corresponds to two basic angles. That's why the result was in terms of had two values. And that's why in this case also, when I give you cosine to be equal to some number, it corresponds to two x's. It corresponds to two x's. That one and the other is just the negative of the given one. Okay? So that's why in this case, and because the x corresponds to two values, we just have here plus or minus like this. When I give you, when cosine is given, when the cosine is given, that corresponds to two values. That corresponds to two values. Now let's learn some simplifications of hyperbolic functions. One rule, whenever you find a ln function inside a hyperbolic function, you know that there will be a simplification in this case. Whenever you find a ln inside a hyperbolic function. Why? Because hyperbolic functions were just exponential functions. So whenever you put a ln function inside exponential functions, you will have some simplification. Okay? So that's why for this expression, we may expand it like this, or we may simplify it like this. I just write it as e power 2 ln x minus e power minus 2 ln x over e power 2 ln x plus e power minus 2 ln x. How would I simplify this expression? We learned before that exponential of ln of something would just give me that something. But whenever that was a direct operation, okay, if e just operates on the ln without any separators between them, we don't have a number here, for example, or I don't divide by a number, or it is just a direct operation. E directly operates on the ln. But in this case, e, there is some separator between the exponential and the ln. So could I make a simplification for this expression? Do you have any ideas how would I simplify this expression? Can I just get rid of this 2 that is on my way to, that is an obstacle on my way to simplify the e with the ln? Do I know any of the properties of the ln that makes me or makes me manage to get rid of this 2. Yes, I will take it as the exponent inside the ln. So that is just e power ln x squared. That is just e power ln x squared. So that's why in this case it will just be like this. So it will be x squared. And that's why the first term is just x squared. And for that one, I'll just take it also. All of these, I'll just take it to be like this. So it is x squared minus e x power minus 2, x squared plus e x power negative 2. For more simplification, I may multiply by x squared for both the numerator and the numerator. So it will just be x power 4 minus 1 x power 4 plus 1. Okay, so this is the simplification of this function. Now remember that whenever you make a simplification, you preserve the domain of the original function, because simplification changes the domain. Now what is the domain of this function? Now remember that here, or there is a condition on x. X is inside ln. In this case, x is inside ln. So that's why x here must be a positive value. We learned before that any ln, there is a condition for any argument for the ln, inside the ln. It must be a positive. It must be positive. Okay? So this is a condition. It is not the domain, because tanh, we learned that tanh had a domain of R. So, okay. So this is exactly the domain. The domain would be x greater than 0. So if I write, or if I make this simplification, I must write that, remember that this expression only works for x greater than 0. I must preserve the original domain of the function after simplifications. Okay? Now if I told you to solve this equation, I need you to solve this equation now. Cosine of 2 ln x equal to 2. I need you to solve this equation. Now give it a try. Use simplifications to solve this equation. You notice here that I have a ln function inside the hyperbolic function. So the first impression is to make a simplification for this expression. The expression on the left hand side. Now let's try to solve it and review your solution with me. I will just make a simplification for this. I will write it as e power 2 ln x plus e power 2 minus 2 ln x over 2 equal to 2. So that means that e power 2 ln x, I will just take the 2 inside the ln. So it will be e power ln x squared plus e power ln x power minus 2 equal to 4. From the cross, it will be equal to 4. So these two functions cancel the effect of each other. So it will be x squared plus x power negative 2 equal to 4. How would I solve this equation? Look at this equation. If I have here x power negative 2. This is exactly x squared plus 1 over x squared. What would you expect me to solve this equation? I would multiply by x squared. So it will be x power 4 plus 1 equal to 4x squared, which may be written as x power 4 minus 4x squared plus 1 equal to 0. Now this is a quadratic equation, but in terms of x squared. I may rewrite it as x squared all squared minus 4x squared plus 1 equal to 0. This is a quadratic equation, an ordinary quadratic equation, which may be solved but for x squared. Instead of solving for x, it is solved for x squared. X squared equal to minus b, which is plus 4, plus or minus square root b squared, which is 16, minus 4ac, which will just be equal to 4, all over 2a, which is 2. This is the law of solving quadratic equations. The law of solving quadratic equations, which is, if you remember, it is for ax squared plus bx plus c equals 0. The solutions are minus b plus or minus root b squared minus 4ac over 2a. This is a known formula for the solutions of quadratic equation. Okay? Now these are two solutions, which mean that x squared equal to 4 plus or minus, that is 12, and I may write 12 root 12 as 2 root 3 all over 2, which is exactly 2 plus or minus root 3. So these are two values. These are two values for x squared. X squared has two values, 2 plus root 3 and 2 minus root 3. Any of these two values rejected? Now you have to look a closer look. If one of them had a negative value, because it may not be obvious, the negative value may not, so I need to know if it has a negative value. This one is positive. Okay, root 2 plus root 3 is a positive value. 2 minus root 3. What about 2 minus root 3? Root 3 is less than root 4, which is 2. So this will also be a positive value. But if I had one of them to be a negative value, it would be a rejected value, because x squared could never be a negative value. Okay? X squared could, so if I had one of them to be a negative value, I would just reject it. So in this case, I would just say that I have x will be equal to plus or minus root of 2 plus root 3, and for this one I will just have plus or minus root of 2 minus root 3. So I have 4 solutions for this equation. But there is a flaw in my argument here. Are all the 4 would be solutions in this case? No. Why? I must check the solutions with the original equation. The original equation, I had a condition on x. What is the condition on x in this case? The x must be inside a ln. What is the condition for any x inside the ln? It must be positive. It must be positive. So any solution must be positive. So that's why I would reject the negative values. Reject the negatives. So this equation would have 4 solutions or 2 solutions only? I will just have 2 solutions for this equation. Okay? So for this equation, I'll just have 2 solutions.